Okay, welcome everyone. In this video, we're going to discuss Abel's theorem as it applies to second order equations. So let's set up the framework. We're going to let L of y be the differential operator y double prime plus p of xy prime plus q of xy. And suppose that y1 and y2 are solutions of the differential equation L of y equals 0. That is to say that that's a differential equation y double prime plus p of xy prime plus q of xy equals 0 on some interval, let's say the interval from alpha to beta in the real line, okay? So y1 and y2 both satisfy this differential equation. Then the Wronskian of y1 and y2 at a point x is given by a constant times e to the minus integral p of x dx, where p is that coefficient function of the derivative term, and c depends on y and y1 and y2 rather, the two solutions of this, but not on t. So the c is independent of t. Thus, either one of two things happens. Either y1 and y2, the Wronskian of that, at x is identically equal to 0 for all x in the interval from alpha to beta, or the Wronskian is never equal to 0 on that interval. Okay, because it's given by an exponential. And so the exponential is never 0. So the Wronskian can only be 0 if c is 0. But if c is 0, then the Wronskian vanishes on that entire interval. And if c is not 0, then the Wronskian won't vanish anywhere in that interval. Okay, so that tells us that if you, for linearly independent, for two solutions of y1 and two solutions, y1 and y2, of a differential equation of this form, then their Wronskian is either always 0 or never 0 on the interval where the solution exists. Okay, so let's see why that's true. It's kind of an interesting proof. Okay, so y1 and y2 both satisfy the same differential equation. So in other words, y double prime plus py1 prime plus qy1 equals 0. And y2 double prime plus py2 prime plus qy2 equals 0. Both of those are true. Okay, so let's multiply the first equation by minus y2. And we'll multiply this equation by y1. Okay, so when we do that, and then we'll add. Okay, so when we do that, we will get, so taking these two, and let's do that and rewrite it. So this will become minus y2 y1 double prime plus, minus py1 prime y2 minus qy1 y2 equals 0. And then on this one, we will get y1, y2 double prime plus py y2 prime y1 plus qy1 y2 equals 0. Okay, and now when we add those two equations, we get 0 is equal to, from these two terms, we get y1, y2 double prime minus y2, y1 double prime. These two terms cancel each other out. And then from this one, the middle one will factor out a common factor of p. And then we have y1, y2 prime minus y1 prime, y2. Okay. All right. So we look at that. Now notice, remember what the Wronskian is. The Wronskian of y1 and y2 is the determinant of the matrix y1, y1 prime, y2, y2 prime. So that is y1, y2 prime minus y2, y1 prime. Okay. And notice that's one of the terms that you have right here. So this is P times the Wronskian. Okay. And now what about this? What happens if I differentiate W? So let's differentiate this guy. I will get y1, y2 double prime plus y1 prime, y2 prime by the product rule. And then here I will get minus y2 prime, y1 prime minus y2, y1 double prime. Okay, so these two terms cancel. And so I am left with y1, y2 double prime minus y2, y1 double prime. Okay. And so now when we look back at this equation that we had at the bottom of the last sheet, compare that, let me not cover this, we see that this equation here is really 0 is equal to W prime, and then I have plus P times, this term is W. Okay, so we have W prime plus P times W. Just using our substitute, exactly what we calculated before. Well, that's a first order ODE for W. And moreover, it's separable, so let's separate it. So this means d capital W dx is equal to minus P times W, or rewriting that, that says dW over W is minus P dx. So that's separated because P is only a function of X, so I integrate on both sides. I get ln absolute value of W is equal to minus the integral of, that should be P of X dx, so let me go ahead and write it like that. And now I exponentiate to solve for W. And remember, when you do an indefinite integral like this, there's always an arbitrary constant. So let me remind you, there's an arbitrary constant that comes out of here, okay? All right, so now when I exponentiate rather, I will get W on this side. On this side, I will get e to the integral, e to the minus integral P of X times e to the C, which is another constant, times e to the minus integral P of X dx. Because e to the C is just another constant, so I write it like this. And that's exactly what we wanted to show. That's it. So the Wronskian is given by the exponential of the negative of the coefficient of the y prime term. And so once you have that, the Wronskian is given by a formula like this, where y1 and y2 are two solutions of the ODE, y double prime plus py prime plus qy equals 0, then that's it. This thing has to be either identically 0 or never 0, depending upon whether the constant is 0 or non-zero. Okay, so that's it for the Wronskian, and showing the Wronskian satisfies this exponential formula. And let me get back to our theorem. So that shows us that the Wronskian satisfies this exponential formula, and therefore either the Wronskian is never 0 or it's always 0, depending upon whether the constant is c is 0 or not. So that's a beautiful theorem that goes way back to Abel, and we'll see how it's used in a bit.